All right. So how the eigenvalue finally looks like? So you just put the T11 and the T12 for the one pair into the term here. Then for the plus term, you got the T11, T22, and it become something like a minus -1 divided by t squared with cosine delta lambda plus r squared. So this is the first term, and the whole second term is here. Yeah, this is pure mathematical. You will so I'll just skip the deduction. So as the detuning increase is absolutely increase is either in short wavelengths or long wavelengths, it doesn't matter. When the delta is large enough, when the delta is increasing, the delta lambda will become lower. As long as it lowers the value of 1 minus 2r squared. The r here is the reflectivity, interfacial reflectivity. All right. So it is the like n1 plus n2 and n1 minus n2, something like that. When cosine theta becomes smaller term, you will see the whole and the eigenvalue become pure imaginary. The second term become negative, so it become it changed from a pure and real number into a complex number because the second term become imaginary. Yeah, since the first term here, this is still real, and but the second term here, because the cosine theta is smaller, it become minus value, so it become a plus value. And okay, absolute value. So like okay, yeah, just say plus value plus and minus a square root of a minus value. So it is a complex number. Okay, so it turns from a pure real eigenvalue become a composite value. So this is not exactly, it should be exponential im pi plus and minus theta, and probably with and another still a real term and something like and phi, something like that together. All right. So the locus with increasing the detuning of 2 points like this. When there's no detuning, your eigenvalue, two eigenvalue on complex plane will be, one it is exponential plus and c, and the other one it is exponential minus c. Yeah, as the detuning increase, this reflectivity, the eigenvalue is become closer to 1. Yeah, and these two values meet when the cosine lambda delta is 1 minus 2r squared. Then it becomes a complex value. So one of them will be like oscillating along the unicircle, and the other one will be oscillating along the unicircle as well. But anyway, the multiplication of two values still need to be 1. All right. So as long as your eigenvalue is still away from the unicircle, yes, along this range, after alternating many pairs, Yeah, still in this rate, after altering many pairs, exponential plus m as shown, still goes to infinity as m increases. But when the detuning is too much, you increase many pair, the absolute value will be no more approaching to infinity. So it doesn't have a strong function in reflecting wave. So the high reflectivity doesn't need to be in a specific wavelength. As long as your detuning is small, it's not too away from the breadth index, the reflectivity still grows as the number of pair increases. Okay, but if the tune and under such condition, you will still get a real number of MEFF, and as the n goes to infinity, the tangent MFF still goes to 1. Yeah, then the MEFF become MEFF 1 divided by the tangent hypertangent C. Or probably you can just call it as a hypercotangent C. Yeah, that's fine. But when the wavelength is assessing a critical value, that when the cosine delta lambda is smaller than that, then your MEFF just become a complex number, and it will be escalating. It will no more increasing. It will be escalating as the amount of pairs. So you will get an MEFF probably and become high and low and high and low. It doesn't goes to an infinite. It goes to approaching a converged value. Alright, so this is how it looks like for two scenarios. For the first case, is that the delta n is large. We let the n2 to be 2.1 and the n1 is 2.5. So the R here is 0.087. Okay. So what did we get? That we just try to calculate the value of arbitrary lambda, then try to plot this relativity like this. You will see when the number is less, it is generally low, and it's always highest when there's no detuning. And as the number increase from 5, 10, 15, 20, or even more, you will find there will be a small range of detuning. Its reflectivity is still approaching 1, while others is deducing and declining when the detuning is away from a certain region. So this acceptable detuning for a high reflectivity, it is called its stop band. Since within this region, within this wavelength region, as the pair goes to infinity, the reflectivity always approaching to 1. Then that means the light will be stopped by this DBR, because the eventually all the light will be reflected outside the mirror, so there will be no light eventually propagating in such DBR. So we'll call it stop band, and the width of the stop band will be also relevant to the delta lambda. This is another case of with a smaller delta lambda, with a smaller refraction index difference. Like we choose n1 is 2.525 and n2 is 2.4. So the delta is much smaller, and the R is also smaller. So you see the criterion for the smaller r, so the acceptable detuning will be also reduced. So you see, with a smaller reflectivity between two interfaces, we still got a stop band with a limited with a smaller detuning, but the stop band widths will be narrower, and you see the accumulation of the reflectivity will also be weaker with pairs. In the case at the left, you can get you will get probably almost a full stop band with 20 pairs of with 20 pairs of alternating layer. But for the scenario with smaller one, you need, even after 14 pair, we still haven't observed the full stop band, so probably you need 80 pair or even more. Okay, so that would for if you are trying to if your purpose is trying to build a high reflectivity, usually you will choose two alternating layer with a small and significant index differences. But sometimes some people were trying to build a DBR with a small index difference. Why? The merit of using the small index difference is that although it is actually more difficult to build the R, and the precision requirement is also more strict. Yeah, it is. You need to control your things very carefully. But however, if you can do that, you might get a low reflectivity under only a pretty small wavelength range. So the mirror loss will specifically lowered under this region. So it might peak the wavelength with a pretty small wavelength region, and this we will revisit this concept in the next week's class. This is the root of the wavelength tunability. All right, so now we are trying to plot everything, like including its final reflectance and its phase of the reflectivity. We will see that the under Bragg's condition, under Bragg's condition, the reflectivity, the phase is 0. So this is pure real. Yeah, when the detuning, actually it start to becoming and start becoming the complex value. So the locus is not total equality. It's only a schematic illustration to describe how these things happen. Anyway, when the phase goes to pi at each side, that means your reflectivity and goes to pi. When it reach pi, you will simultaneously get the reflectivity goes to 0. So this will becoming a good entrance slit for the light excitation. Yeah, since if you have a DBR, you have a laser, you want to excite there, and you already design the proper DBR on both sides. So if you're trying to shine a light at here, although you can excite your material, but it will be stopped by the DBR. So if you want to do a optically pumped laser, we usually trying to excite your structure along this wavelength. The light can directly goes in and inside the AT region, and the generated the photons then can start bouncing back between DBR to make a optically pumped laser. But anyway, with the mathematical relation, we can try basically evaluate something called a stop band. Stop band we can consider as the wavelength, the wavelength range or the frequency range of the unity when the R becomes equal to 1 when the m goes to 0. M goes to infinity. So if you deposit infinity pairs, you will get a range which the reflectivity to be 1, and that we call the stop band. So since this is also, probably I can leave you as your challenging homework. But anyway, you can anyway. I just tell you the result. It is between the two poles of this detuning. Yeah, if you take the complex variable, you might understand what I'm talking about. Okay, so it will be 4f0 divided by pi times arc sine n2 minus n1 n2 plus n1. So according to this equation, as long if you have a large delta n, you will also have a higher stop band. This is from the point of frequency. The stop bandwidth in wavelengths is similar, since we can take a total differential of the light of speed. So you will get the delta lambda over lambda 0 should be equal to delta f over delta f0. It is still 4 over pi times arc sine and n2 minus n1 divided by n2 plus n1. But this is, remember, this does not consider dispersion. So in reality, the stop bandwidth will be smaller than this value. And it deviates more when the dispersion is severe. So this is only a reference for a perfect scenario that the two-layer, the refract index is very consistent for a broad range of wavelengths. Okay, so at least you can still compare the in semi-quantitative way with different design of your alternating layers. Okay, so this is the one-page summary of what we've done. So first we can calculate the R for the interface, then build up the transmission matrix with 4 elements by the R and the theta, and with the theta plus and minus, it is the optical path in each layer. In each layer. Then after some transformation with eigenvalues, we get arbitrary pairs, so gather the 4 elements with the expression like this. Then rearrangement with new parameters called the large delta and NEFF. We further write it down the matrix elements of grating here. Then we get the RG of this is the final result, and trying to plot them with different wavelengths. Then you got the spectrum like this. This is the common DBR spectrum you will observe in any laser textbooks.